Good morning, everybody. Welcome to a sunny but cold morning of Chem 1211 with your host, me, Dr. White. Hi. All right, let me remind you, and let me get it up. Today, when I'm through with class, and maybe it might be a little before 11 a.m., I will send out an email to each of you, and that email will have the password for quiz number 3 PDF file. You can download this from the assignment area of Blackboard. And let me go to student view. If you click over, everybody see Blackboard on my screen? Thank you. If you click on assignments, and you'll see quiz number 3. Here's the PDF file. In case you forgot, here are instructions for how to upload your answers as a single PDF file. And if you don't have a scanner, you can use the app Cam Scanner. A number of students have. Use the free version. Don't waste your money. You don't need all the bells and whistles on a paid version. So take quiz number 3. I'll be sending out, let me exit this. Go back to the announcements. You'll have until tomorrow morning, 11 a.m. to take quiz number 3 and upload your answers. I reserve the right to subtract, yes, up to 25 points from your quiz number 3 point total or total points for anyone who does not follow instructions. That means upload your answers as a single PDF file and who doesn't get your answers uploaded on time. Quiz 3 has 4 pages, 8 problems, and I just noticed something. Hold on. I better go back to assignments. Let me check something real quick. Yep, I forgot something. You can watch real time how Dr. White and I forgot to upload the periodic table. It's now there if you don't have the one I've done in the past. So anyways, let's go back to announcements. You'll have until tomorrow to hand it in. By Sunday, 1 p.m. or a lot earlier, I'll have your test quiz 3 scores in Blackboard. By that time or earlier, I'll also email you individually an email containing how many points you receive for each answer on quiz number 3. Next Monday, I will go over quiz number 3 answers, but I'll cut it out of the Zoom meeting. And then if you can't make that, come to my office hours. If you can't come to my office hours because you're working or other responsibilities, don't forget to email me and I'll set up a private Zoom meeting. All right, so don't forget today will be quiz number 3 later today. All right, one other thing I don't have there, but I've mentioned before. If you do not have a printer, by the way, this is a nice HP printer right there, and that cost me from over a year ago from Staples, just under, well, about $199, which it's just a laser jet, but it also has a scanner and a fax, who does faxes these days? You make a scan and make a PDF file and email it. But anyways, if you don't have a printer, on a piece of paper, a couple of pieces, don't make it too small so I can't see it. Spread it out. You can have more than one page. Put down your answers for each problem. Listen carefully. If you don't have a printer, you do not have to write down the actual questions. All you need is the question number and your answer. And one last thing about quiz 3, or actually two things about quiz 3. Underneath your name, it will say, please use proper significant figures for all calculated answers. Please use all atomic weights, the three significant figures. I'll take off points. By the way, I got out of my 3 significant figure rut on this quiz. But don't forget that. And what was the other thing I was going to say? I forgot. There are 2 things. Wow, that just went zoop out of my brain. But don't forget to get it in on time. Oh, I know what I was going to say. On all my quizzes and tests, it pays to show your work. If you make a mistake and I can say, oh, you did this wrong, but it was like 15 points and it was just a minor mistake, you can get 13 or 14 points. If you just put down an answer and it's wrong, you get 0 points. You don't want that. Show your work. All right. Any questions about quiz 3? All right, another thing I should mention, by Friday, if not earlier, I will have posted the information about quiz 4. Quiz 4 will be next Wednesday. Normally, if I were face-to-face, quiz 3 and 4 would be combined as a test, which I give at one time next week. But because of the way the department has set up this class now, you have to take 2 tests. Later on, you'll have test 2 at COD, and I can't give tests online. I can only give quizzes. You didn't see that. But anyways, quiz 4 will be next week on solutions. I've covered all the material on solutions. Next Monday, I will go through the solutions problem set. Next Monday, I will also do my review for quiz 4. And also, by the end of the week, I'll have quiz 4 review and quiz 4 important information, which is on solutions in Blackboard. And one final last thing. Next Tuesday is election day. It will be a holiday. I don't know if they call it a holiday. Well, that is a holiday in a sense, but it's a special day in Illinois, and there will be no school, no classes, especially mine. So what I'll be doing is the lab we normally do next Tuesday, I'll have a special Thursday class that will go through that lab, and I'll videotape it, so if you can't make it the Thursday, you'll still be able to see it on my YouTube channel. But I'll remind you next Monday. And finally, a personal note, brave men and women have died. Yes, have died, so we can vote. You should vote. I'm not telling you who you should vote for. I'm just saying every American should vote. You can vote this week. Early voting is throughout Cook County, and I believe DuPage and Kane County, I live in Cook County, have it also. I know Cook has it, and I think DuPage and Kane County have it also, but they have on-site registration, voter registration, but you check. If you're registered, please, please vote. This is probably one of the most important elections in our lifetime. All right, with that, as I said, I'm done with all the material from solutions, so it's time for a new chapter, unless anybody has any questions. All right, thumbs up, people. Everybody see chapter 15. Thank you, Gianna J. All right, now, just a note, the way the book is written, if you have the book, I disagree that chapter 14, acids and bases, should be before chapter 15. I would do it the other way around, and so in my class, I will. Now, chapter 15 deals with what's called chemical equilibrium and also rates of reaction. And you'll learn about what that means this chapter. Now, note, extra material will be presented that is not in your book. And I will. So let's get into this. When we talk about a reaction, and by the way, switch is on, but this is for quiz 5, not quiz 4, which is coming up in a couple of weeks. So the end of the semester isn't that far away. Whoa. But anyways, this is quiz 5, not 3 or 4, but the switch is fully on. Click on. All right. When we talk about rates of reactions or just chemical reactions in general, there's something called the collision theory and chemical reactions. As you did last week in lab where you were investigating, did a chemical reaction occur? What's necessary for a chemical reaction to occur? You have two things. How do you make them react? To make new molecules. Now, why is this important? Because just look around your daily life. Anything you see right now behind me and everything is made up of atoms, that's made up of molecules that make molecules that are made by chemical reactions. There's a can of WD-40. The stuff in there is made from chemical reactions. I have a couple external big hard drives there. The plastic and other material, that's made by chemical reactions. So what do? If you're Harry Potter, do you take out your magic wand and say the words and make a chemical reaction? Nope. Chemistry is not magic, even though sometimes it does seem magical. Ooh, that was a good line. But anyways, how do you make a reaction occur? Well, let's look at the collision theory and chemical reactions. Now, what is this collision theory? It's a set of statements that give conditions that must be met before a chemical reaction takes place. So let's get into it. All right, time for Dr. White to be subtle. Don't you like it when I'm subtle? Hint, know this. All right. Well, the first statement that must occur, so a statement of something that must be occur when you have two chemicals reacting together to form a chemical reaction is molecular collisions. Reactant particles must interact, collide. By the way, IE is shorthand for Latin that's translated into English, meaning that is collide. So reactant particles must collide before you can have a chemical reaction. So if I have a chemical reaction like this, remember A and B are the reactants. which I'll sometimes, a lot of times, call starting materials. And C is the product. And in order to make C, A and B have to collide. That's why you mix chemicals together. That's why you stir things, because you make the chemical reactants collide. So think about it. In order to make C, A and B have to be mixed together and they collide. How do you like these special effects? Boom, collide. Hopefully they don't go boom. But anyways, now the next statement you should know is called activation energy. Now, there are different ways of saying this, but colliding particles of chemicals must possess a certain minimal total amount of energy called the activation energy if the collision is to be effective. And what we mean by effective is have a chemical reaction occur. So when two come together, particles, if they just come together and go, think, that may not be enough energy for a chemical reaction to occur. They have to have the minimal amount called the activation energy, and they come together and go boom, and they react. Now, another way of thinking of energy, I'm going to sneeze in a second. Hold on. Nope, stop for a second. A couple other ways of thinking of activation energy. That's the amount of energy to break bonds between atoms of reactants. That's from your book. But anyways, another way of thinking of activation energy is the minimum combined kinetic energy. That means how fast they're coming together. That reactant particles must possess in order for their collision to result in a reaction. So the key thing is activation energy. That's the minimum energy that particles have to have when they collide to form a chemical reaction. And finally, chemical collision theory, you need to have collision orientation. When certain particles collide, they must come together in a certain orientation unless the molecules are single atoms or very small symmetrical molecules. So what that means is things like in your body, your enzymes, when they form reactions or other things form reactions, they have to be oriented properly. And what's an example of that? Hold on while I get it out. I always carry my house key in case I have to go out for a second. Here I have a key. And if I have a lock here and I put the key in upside down, it's not going to go in and lock my door. It has to have the right orientation. Also has to have the right bumps here, but that's another story. But if you put it in the right way, click, and now the door is open. So, like a key, molecules, by the way, remember I told you I'm a flashlight nut? Is that a cute flashlight? It's got two different brightnesses. Is that cute? But anyways, it's got a rechargeable battery in there. When you have molecules coming together, they have to mesh together in the right orientation. Otherwise, they won't react. So that's the important feature of the collision theory of reactions. And let's go through it again. There are three statements you should know. Here's number one, and that is for a reaction to occur, molecules must collide. That's why it's called the collision theory. So, number one, for a reaction to occur, like A plus B making C, A and B have to collide. You got to mix them together so they interact, and we call that interaction colliding. All right, so the first step you should know, molecules should collide or have to collide to have a chemical reaction. Now, the next statement you should know or aspect is for a chemical reaction to occur, colliding atoms, molecules, or any combination thereof must possess a certain amount of energy, which we call the activation energy, to have a reaction. And that's what we mean by if the collision is to be effective. In other words, if they just go, think, no, second, they gotta go wham. I don't know about wham and ding, but you get the message. They have to have a certain amount of energy called the activation energy when they collide for a reaction to occur. And the third one is collision orientation. And when you have certain molecules that are larger, which when they come together, in order for a reaction to happen, they have to have the right orientation. Like my key, if it goes in upside down, it's not going to go in. Well, even though they collide, they have the right amount of activation energy. If they're not lined up properly, they won't react. And an interesting sidelight, many of the reactions going on in our body, and especially those interactions going on with medicine. That's why certain medicine is very expensive, because it has to have the right orientation and shape to be effective because of the collision theory of reactions. And medicine solving problems you have, those are chemical reactions. So one more time, real quick, you should know the three statements or how to describe the three aspects of the collision theory of reactions. One, when in order to have a reaction, reactants must collide. Two, when they collide, in order to have a reaction, the particles, molecules, or atoms must have enough energy. And you should know that energy is called activation energy. And finally, for larger molecules, when they interact, collide with the right amount of energy, they also have to have the right orientation in order to have a reaction to occur. And that's the collision theory. So now you know about reactions. Now, something I haven't talked about yet, which I will now, are called reaction rates. And let's go to our old reaction, A plus B makes C. Now, when you mix A and B together and they interact and they have the right orientation or enough activation energy, do you make C just like that? Or do you have to wait a long, long time? Well, it turns out it could be both. Certain reactions are very quick and others are very slow. Now, what are quick ones? There's certain reactions that occur that happen within a billionth of a second, called a nanosecond. 1 billion, I mean, that's fast. That's quicker than I can blink. That was almost a half a second. I don't know how many lots of nanoseconds, but it's called diffusion control. That's very quick. And then there can be reactions that are very, very slow. In fact, at one company I worked at, a reaction I was responsible for, when they ran it at the chemical plant or in a lab, from the time you started mixing things together till you were done, it took about, are you ready for this? About 34 hours. Yep, more than 24 hours, almost 36 hours. And in a chemical plant, they never close, at least the ones I've worked at. They work around the clock. You have different shifts. And at this company, the workers did 12 hours and they went home for 12 hours, came back, 12-hour shifts, 5 days a week. And they had shifts, so there was also weekend shifts too. And they alternated, but that reaction took 34 to 36 hours. I can still picture there. I would go there and supervise. That was part of my job for some new reactions or when they were having problems. And when it was a long reaction like that, 36 hours, guess what? I had another chemist who worked for me with me. I do 12 hours, he'd do 12 hours, then I do the final 12 hours, help supervise. And the bad thing was, if there was a problem and it was 3 in the morning, and this was in Louisville, Kentucky, I get a phone call at my hotel I was staying at. I was only about 15-minute drive or less from the plant in Louisville. But anyways, I get a phone call. What do we do? And it'd be my chemist who didn't really know what to do, or a lot of times with a lot of money involved. When you run a reaction in a chemical plant, this one, that was about $180,000 on the line, and I get a call. And I learned to wake up real quick. And actually, what I used to do, they called me at 3 in the morning. I said, is it going to explode? No. All right. Call me back in 5 minutes. I'm going to splash some water in my face and wake up. And 5 minutes, they'd call back. I'd be awake. What's the problem? Then I'd make a decision. A lot of times they knew what to do, but with $180,000 on the line, they were afraid to do it. I was never afraid to do it, and I never made a mistake either. Thank you. Not to bring religion into the classroom. All right, let's talk about the rate of a chemical reaction. What does that mean? That's the rate at which reactants are consumed. The term consume means used up or disappeared or changed into products. The other way of defining it is that's the rate at which products are produced in a given time period in a given chemical reaction. So we have something called the rate of reaction. Another way of defining it is measuring the amount of reactants used up or amount of products formed in a certain time period. So you can have A and B and react it to make C. And you can time it. How long does it take to get rid of all in A and B? That means consumed. Again, when something is used up, is gone, because A and B react to make C, we call that A and B are consumed. And you can measure that and say, well, it took all of A and B to be consumed 5 hours or 2 seconds. And that tells you whether you have a very fast reaction rate or a medium, or if it took 28 hours, the slow reaction rate. And turns out knowing reaction rates are very important. Now, what can influence the reaction rate? How fast or slow a reaction goes? And you should be familiar with these. Hint, one is the nature of the reactants. Are they solids? Are they liquids? Or are they gases? Now, solids And there's a branch of chemistry called solid state chemistry. And that deals with reacting solids together. If you put two solids together, hold on. Better. Two solids. How long does it take for this to react? Use your imagination. These are molecules or solids. And turns out that's not a trivial question. It's an area I have never worked in because I've never worked with chemical reactions that everything was a solid. Now, there's other things that will, when we talk about the nature, if they're liquids. And that's one reason why all the reactions I've done have been either in liquids or gases and liquids, or solids mixed and dissolved in liquids. And those go a lot faster, most of them, than solids reacting together. And finally, gases, a lot of the gases, that's the quickest reacting. But you have mixtures of these where you have gas in a liquid, solid dissolved in a liquid. So what it is will affect how fast or slow a reaction goes, which we call the reaction rate. Now, another thing that will affect it is the reaction concentrations. Concentrations means how much there is of something. And generally, if you increase the concentration of the reactants, that will increase the reaction rate or rate of reaction. So the more you have of the reactants, meaning the more collisions that can happen, collision theory, yep, the faster it can occur. So if I were to take my reaction, A plus B makes C, if I put in a lot more A and B together, that should make it most of the time, not all, go quicker. Now, something I shouldn't point out, and I'll talk about this later. How do we show concentrations in a reaction? Like this. When you have a bracket, the formula and close bracket, that means moles A per 1 liter of solution concentration. And the higher A is, the higher the concentration, the more there is. So we'll talk more about this later. But what will affect the rate of reaction? And that is the reaction concentrations. If you put more of the reactants, starting materials, that mostly will make it go faster. Not always. Now, I don't know if I mentioned this, I might have. When I was an undergrad and even grad school, if I were taking notes in my left margin, if it was important, I'd put a star, 2 or 3 stars. More stars, the more important. If it was really important, I'd put the stars and I'd write IMP, shorthand for important. And this is important. What is another way to make a reaction rate increase, make a reaction go quicker? And that is the reaction temperature. And this is called the rule of thumb. If you increase the, I'll talk about in a second, the rule of thumb, increase the reaction temperature, increases the kinetic energy, which means the collisions are even more forceful. And what you should know, this, and that is the rate of a chemical reaction doubles for every 10 degrees increase in the reaction rate. The rate of a chemical reaction doubles twice as fast for every 10 degrees C increase in a reaction temperature. So for most, now, a rule of thumb is not a law. A law is always true. A rule of thumb, 95%, maybe even a little higher, it's true, but it's not always true. In fact, when I was at one company, there was one reaction that I had to supervise to make a product that we actually had to cool it down. It was just the opposite, because if you heated it up, it went slower. And that was because of something we'll talk about in a little while. But you should know, first of all, reaction temperature will affect the rate of reaction. When you increase it, it goes faster, the reaction rate. And a rule of thumb, the rate of a chemical reaction doubles for every 10 degrees increase in temperature. Now, practical thing, if you cool things down, a lot of times that slows down the chemical reaction. How many of you ever had problems with your car battery when it gets super cold outside? In fact, what was it? 2 or 3, no, it was what, 3, 4 years ago when we had brutal cold here in Chicagoland, below 20 below, and that wasn't the wind chill, that was the temperature. In fact, both COD and where our other school I teach, ECC, closed. It was so cold with the wind chill, I wondered about the fluid around your eyes, would it freeze? And it might have. But anyways, what important thing happened back then, people who had electric cars with big batteries in it were finding out in the super cold, the distance they normally could drive before they had to recharge their battery dropped really far. They couldn't drive as far before their battery went too low. What happened? Well, and it happens in a regular car too, in a car battery, to start your car. Inside your car battery is a chemical reaction going on to make the electricity. And guess what? When it got colder, that reaction slowed way down. And because of that, you had less electricity to either make your car go if you had an electric car, or guess what? Start your car if your battery was out all night in the cold. If it wasn't fully charged and you made it go slower to reaction to make the electricity in your battery, it just wouldn't start your car. And that happened a lot. Now, the last, I don't know, yep, hold on. Now, the last thing I'll talk about, what can make a reaction go faster, is a catalyst. And you should know this. You should know the definition of a catalyst. Now you know it's important. You should know, what is a catalyst. It's a substance that increases the reaction rate without being consumed. So if I have a reaction, oops, D plus E goes to make F. And it has a certain reaction rate. Let's call it X. If X is really large and I want to make it faster, I'll add a catalyst. And a catalyst, the new rate is Y. And Y, if you got the right catalyst, and that's important, but we won't go into that in this class, will be much shorter, smaller than X. That makes a reaction go quicker. So if you want a reaction to go quicker, you add a catalyst. Now, I'm going to go well beyond my knowledge of biology, but your enzymes are catalysts. They're special catalysts that make reactions in our body go quicker. Now, at one company, a group of reactions we ran, in other words, made products. If you didn't have a catalyst, you could wait a month or two and you get very little product. With a catalyst and plus a higher temperature, it was done in 4 hours. So a catalyst makes a reaction go quicker, but the catalyst never becomes part of the product, meaning it's not used up or consumed. You get it back. Now, if you look under your car or somebody else's car, by the engine exhaust, you'll see a structure. That's the catalytic converter. How many of you have ever heard of a catalytic converter in a car? I see one of you have. Well, that's a device that has a certain catalyst in there, and it's made with platinum and palladium, which means it's very expensive, which is why people, when they first came out, were stealing them from the cars and selling them to other people to reclaim that platinum and palladium, make a lot of money. In fact, recently in the last couple of months, certain parts of Chicago, they're doing that again. And it's called a catalytic converter because there's a catalyst in that device that converts any of the carbon monoxide from your engine when it does a chemical reaction into carbon dioxide and water. And that's called combustion. Ooh, you learned about combustion yesterday. So let's see if I can find something real quick. Everybody see on your screen images of catalytic converters. And here, right here, you have a catalyst, and the gases, hydrocarbons and other things, come through and they react with the oxygen that's also in there, and that converts it into less dangerous things like water, carbon dioxide, and nitrogen. And it's called a catalytic converter because it's converting bad stuff into better stuff. And it's using a catalyst. So next time you're with some friends, you can say, you know, our car has, if you're in a car with friends, neighbors, or loved ones, you know, our car has a catalytic converter, and a catalyst in there makes the reaction with oxygen to react bad chemicals coming from our engine to safer ones. Nah, don't do that. People don't want to hear chemistry when you're driving in a car with them unless you're with another chemist. Now, if I look at the clock, I think let's take a break, slightly longer one, like about 30 seconds longer. And that will be, let's come back at 9:50, 55, about 5 minutes from now, give or take 30 seconds, and we'll continue. Don't forget, when I'm done today, I'll send out the password for quiz number 3. See you in 5. I'm back. All right, let me remind you, and I think we might even end a couple minutes early. So you can start on, I can get the password out for quiz 3. But let me remind you, after our class today, I'll send out quiz 3 password. Let me remind you, next Monday, I'll go through the solutions problem set, and I'll also do the review for quiz number 4, which will be next Wednesday. Don't forget, next Tuesday is election day, and COD in all schools in Illinois will be closed, a lot of other things too, so you can go vote. And with that, let's get back to chemical reactions and their rates. Now, we're talking about a catalyst, and a catalyst is a substance that will increase the reaction rate without being consumed. Now, consider the following. Say you have a reaction X plus Y come together to make XY. Now, what if it's real slow? And this I won't put on a test, but it gives you an idea of what's happening with a catalyst. Now, if it's slow and you want to make it faster, add catalyst C. Am I creative or what? Don't answer that. All right. So what happens when you have a catalyzed reaction, you're using a catalyst to speed up the rate of reaction, how fast you make things. X can react with C very quickly to make XC. And now XC reacts very quickly with Y to make XY. So the overall, and you get back also C. So the overall reaction is X plus Y makes XY. But by going through these 2 steps with the catalyst, it goes a lot quicker. Now, I'm going to be talking about something right now that I don't think is in this chapter in your book, but I think it's important to talk about. And that's an energy diagram. Everybody see my whiteboard now? Thank you, Gianna W. All right, now, an energy diagram is a way of showing in a diagram, a graph, a reaction and its energy. On the x-axis, in case you forgot, that's this one, we have time. On the y-axis, we have energy. Let's look at the reaction A plus B makes C. Now, molecules possess energy. I'll talk more about this later on this semester, but each molecule has a certain amount of energy due to the chemical bonds involved or the electrons. And if we look at A and B, let's assume it has an energy like here. A and B together have this energy. Now let's assume for this example, when you make C, it has more energy than A and B. And this is C. So after starting here to get to here, it takes a certain amount of time. Now here's what an energy diagram teaches us. To go from A to B to C, you have to have a certain amount of energy. You go up and then you go down like this. And this is an energy diagram. Now, an important thing you should know, where you start right here at A and B, this distance right here is the activation energy. You start here, you end up, let's say, right here. That distance, that amount, the difference from where you start and where you end up is an activation energy. Now, if I have A and B making C, it takes a certain amount of time and energy. Now, to make this go quicker, if I had A plus B plus C, let's call it a cat, to make C, it's not a cat, it's catalyst, that's short. What happens is now a catalyst lowers the activation energy. Actually, I should have written this. Hold on. I should not be lazy. And the catalyst really doesn't interact to form the energy, so I really shouldn't have this here. And what I'm talking about, part of this is thermodynamics, which is a challenging course. And here, and it doesn't look this way in my diagram, but in real life it would be. This goes faster. Why? Because you have a catalyst present. And the catalyst lowers the activation energy. And you should know get the right color ink here. Everybody get the message? You should know, how does a catalyst work? A catalyst works by lowering the activation energy, also known as E sub act, ACT. So when you use a catalyst, it makes this blue activation energy smaller than this. It's easier to go up the hill and over and down to grandmother's house. How many remember that? Over the hill, up over the hill and over the dale to grandmother's house we go. We didn't have to do that for my grandparents. There are no hills in Illinois around Chicagoland, really, to speak of. But anyways, how does an catalyst work? It lowers the activation energy. As I mentioned earlier, there are a lot of catalysts in our daily life. In the chemical industry, we use them. In your body, Mother Nature uses them. All of your enzymes, yep, all are catalysts. They're there to make reactions go quicker, to keep us alive and to make things like what's left of my hair and other things. But you should know when we're talking about what factors make a reaction go quicker or affect the reaction rate. The nature of the reactants, whether it's a solid, liquid, or gas, will affect the reaction rate. The concentration of the reactants, how much you have, will affect the reaction rate. Usually it increases it most of the time. And the reaction temperature will affect the reaction rate. And you should know the rule of thumb, oh, it's on this thumb, sorry. The rate of a reaction doubles for every 10 degrees C increase in reaction temperature. So you should know that the rate of a chemical reaction, most of them, that's why it's called the rule of thumb, not a law, but the rate of a chemical reaction doubles for every 10 degrees C increase in reaction temperature. And finally, you should know that a catalyst will make a reaction go quicker. And this does that by a catalyst works by lowering the activation energy. I'll say it again, as it says on the screen. See, you should know this. And a catalyst works by lowering the activation energy. Now, this I don't believe is in your book, so let's go through it. And remember, I'm talking about it. And this is something, again, for quiz 5, not quiz 3. You should be taking later today, or quiz 4 next week. Now, one way of classifying chemical reactions is using the terms exothermic and endothermic. Being subtle again, and know this. All right, what's exothermic? What's endothermic reactions? Well, thermic means something about heat, energy. And an exothermic reaction is a reaction in which energy is released as the reaction occurs. Exothermic reaction is a reaction in which energy is released. Now, how many of you have ever heard of exoskeleton animals? Anyone? And exoskeleton means their skeleton is on the outside of their body. And exo here means the prefix exo, outside or given off, and thermic means energy. Now, the other type is endothermic. An endothermic reaction is a reaction in which a continuous input of energy is needed as the reaction is occurring. Another way of saying that is endothermic reaction, endo, in, taking in, I like my special effects, Endothermic means you have to add energy to make a reaction occur. So we have two types of reaction. Exothermic reaction, it gives off energy as the reaction occurs. Endothermic, just like our skeleton, this is endoskeleton inside our body, you have to add or takes in energy for a reaction to go. Ooh, look at the bottom, a note, seaboard for activation energy graphs. I better get to work. I'm being too subtle this morning. Again, this material is for quiz 5. Now, you should know this. Let's look at the two different types of energy diagrams. So we have our energy diagram with the x-axis being time, reaction time. Sometimes people call that reaction coordinates. I like time better. And the y is energy, or you can is energy. Now let's look at a reaction. A plus B makes C plus heat. Now, there's one thing called conservation of energy. You never create or destroy heat energy in a reaction. So the amount of energy in A and B on this side is equal to total energy C plus heat on the product head of the arrow. Again, you never destroy or create energy. So the total energy in A and B is equal to the energy of C plus heat. So let's assume A and B has an energy like this. And on the energy diagram, we don't specifically show heat. Now, if the total energy of A and B has to be the total energy here, C is going to have less energy than A and B, because you're going to lose some of the energy on the right head of the arrow as heat. It's given off. So let me say it again. Both sides have the same total amount of energy. If A and B have this for an exothermic reaction, C has less energy. That's why this is lower. Here's A and B, lower, less energy is C. And why is that? Because this heat energy is given off. And just like I showed before, you have to go over the hill and down the hill to grandmother's house to go to make C. And you should know, where is the activation energy on this diagram? Is right there. And this is an exothermic reaction because energy, in this case, I'll call it heat. I could have called it energy, but for the most part, we see it as heat. Heat is energy, is given off. That's why this overall reaction is A plus B makes C plus heat. And because of the conservation of energy law, the total energy on this side is equal to total energy on that. A and B have a certain amount of energy. Now, this side, the total energy is C plus heat. If you take away the heat because it gets given off, C is going to have less energy for an exothermic energy diagram than A and B. And it has to go over the hill and down to C. And from where it starts to the top of the hill, it has to go over. That's the activation energy. Hint, you should know how to draw the activation, the energy diagram for an exothermic reaction. Hint, you should know how to draw the energy diagram for an exothermic reaction. And again, I'll go through it. You start out with A and B. First of all, on the y-axis, you always have energy. On the x, I put time. Arbitrarily, I say A and B has this energy. Because it's exothermic and we give off heat, C and heat has to be the same energy in A and B. If you lose some of the energy as heat on the A, C plus heat side, C will have less energy, meaning the line is lower. Remember, energy goes from 0 up to whatever. And this is 0, and this is 0. And that's how you draw it. Remember, from where you start, A and B, to the top of the hill here, that's called the activation energy, which we show as E sub ACT. This is for an exothermic reaction, which gives off heat as the reactor energy as the reaction occurs. Now, here we have an endothermic reaction, and hint, you should know how to draw this. All right, here we have a reaction, D plus E make F. For it to be an endothermic reaction, to make this go, you have to add energy. And for this class, I'll call it heat. So heat plus D plus E makes F. The total amount of energy here equals the energy, this side, the reactants plus heat equals the product F, energy. So let's look at the energy diagram. Now, if we look at this, the total energy on this side equals the total energy on this side. Now, D and E without the heat have a certain energy. But the total energy on this side right here is D and E and heat. So that's equal to the total energy on this side, the product side. So even though D and E have this energy, F has more energy than D and E because you have to add the heat. And that's the total energy here equals the total energy here. So F will be higher energy than D and E because some of that energy to get to F is provided by the heat you have to add. And once again, we go over the hill and down again. And the activation energy is where you start to the top of the hill. And that's for the energy diagram for an exothermic reaction. And hint, you should know how to do this. So let's go through this again. When we talk about reactions, one way of classifying reactions, chemical reactions, is by the terms exothermic and endothermic. Exothermic reaction is a reaction in which energy is released as the reaction is given occurs. Another way of saying that energy for this class means heat. And heat is a form of energy. And not only for this class, but for most of chemistry, when we talk about energy in a chemical reaction being released, it's heat. Now, you could have light, but I've never worked with one of those reactions myself. Now, the other type of classification is endothermic. And look at the prefix, exo, something is given off. Thermic means heat or energy, like temperature, thermometer. And endo is taken in or absorbed. And again, thermic is heat, energy. And an endothermic reaction is a reaction in which energy, a continuous input of energy, is needed as the reaction is occurred. Another way of thinking of it is it's a chemical reaction in which you have to add heat, energy, to make a reaction go. And if we look at the energy diagram, which you should know how to draw the energy diagram for an exothermic reaction. And how do you do that? We have A plus B makes C plus heat. Here we have our energy diagram. The y-axis is energy. The x-axis I call time. Sometimes you'll hear the term reaction coordinates. I don't like that, so I use time. And A and B, heat, equals the product total energy, always equals the reactant total energy, or vice versa. Reactant total energy equals the product energy total. Now here, our reaction is A plus B makes C plus energy, and I'll call that heat. And A and B, I arbitrarily says, has this amount of total energy. Now, because C plus heat has to be equal A and B, heat, energy, some of that energy is lost as heat, so C is below, lower energy than A and B. Then you have this little hill that you have to go over to get to C, and the height of that hill is called the activation energy, and you should know it as E sub A. Now, the other diagram is an endothermic reaction. Endothermic, you have to add energy. And here, the reaction I'm showing you in general is heat plus D and E make F. And good news, you can come back and watch this video a couple times, this part, if this is a little confusing, or don't forget, I have my office hour tonight from 6 to 7:15. You can come by, questions this, or if you're taking quiz number 3, if you have any questions, ask. Also, this afternoon I have to teach, and I also have to make a quick errand, but from between 11:30, 11 and 1, I'll check my email once. And after 4 o'clock, about every 2 hours, till about 9:30, I'll check my email. So if you have any questions about quiz number 3, and also tomorrow morning, but I have to do an errand at 9. So in the morning before 9, I'll check my email. All right, now for an endothermic reaction, that means you have to add heat to make it go. You have heat plus D and E make F. And the energy diagram also is y-axis is energy, x-axis is time. Let's assume D and E have a certain amount of energy. So I draw it here. How much energy does F have in relation to D and E? More, higher on this graph, or less? Well, the total energy, heat plus D plus F plus E, let me do that again, bad Dr. White. Heat plus D plus E has to equal the total energy F. Well, since you have to add some heat energy, D and E has less energy than F, or another way of saying it, for an endothermic reaction, the product F has more energy, and that's why it's higher. And you have the same sort of hill. It doesn't matter how pointy you make your hill, going from D and E to F, and you should know from where you start out, D and E, to the top of the hill is the activation energy, the amount of energy you need to make a reaction go, because it's got to go over the hill to get to F. Now, because I'm going to give quiz number 3 today, you know something? I think now is a good time to, hold on one second. Oh, my keyboard just fell down on me. All right. Now is a good time to stop, a good time to take a break, like stop the class. I'm going to send out the email with the password for quiz 3 in a little while. Don't forget, you have to hand it in, upload your answers for quiz 3 by tomorrow, Thursday, 11 a.m. I will have my office hour tonight. If you have any questions, or email me about quiz 3. Don't cheat. I have things in quiz 3. I'm pretty sneaky that I'll know if you cheated, and I will do what's in my syllabus if you do cheat, and I can prove it. Trust me, I can. I've unfortunately have done it before, both online and face to face, where I've dealt with the dean, my dean of math and science, along with the dean of students. Not fun. I don't want to do that. So please don't cheat. So with that, I'm done for today. Don't forget, hopefully you handed in the lab yesterday that you did last week. If not, get it done real quick today or tomorrow. And with that, I'm going to say, Gang gesund. I'll see you on Monday, unless you come to my office hour. Bye now, and good luck on quiz number 3.